All right, good morning. So we'll start off with some good news. Lab 6 is gone, so yay. Yeah, I spoke to Ashton last night. So Lab 3 got extended too. It's extended a week, so you have 3 weeks for it. So that's pretty sweet. Then there will be a new Lab 4 that I'm making, so you'll get a taste of my labs. It shouldn't be terribly bad, yeah.
So how's Lab 5 going to look like?
Sorry?
How's Lab 5 going to look like?
Yeah, so Lab 4 will be new, and then we're essentially going to combine old Lab 4 and 5, which was like, first you made like a concurrent web server and then you added caching to it in Lab 5. So we'll give you a concurrent web server that probably has like a little mistake in it you need to fix. That should be like the weak part of it, and you'll have 3 weeks for that combined lab. So it'll be a new Lab 4, then we're gonna combine old Lab 4 and 5, give you some code, and make that 3 weeks as well. So one last lab, that's all good, and you'll get a taste of my lab. So hopefully my lab will be slightly less time consuming, let's say. So yeah, and that way Lab 3 due date doesn't conflict with next week's quiz and all that fun stuff. Also, the other class is behind, so scheduling will not be on the quiz. So this is just bonus for next quiz. And then next week, I think I'll start off the week with like a Lab 4 primer. So Lab 4 will just pretty much be combining a whole bunch of system calls we saw earlier. We need practice about it anyway, so I'll do a Lab 4 primer. And then if you let me know on Discord anything else you want to do, because we essentially have 2 free lectures, we can turn into quiz review or just do whatever, do more locking examples or something like that. So let's get on with today's lecture, and then we can chill out for today's lecture. So we'll be talking about more scheduling and what actually happens. So one of the things the student mentioned last time is, well, if we have scheduling and a bunch of processes, we might want to add priorities. Some processes may be more important than other ones. So you could assign each process a priority, which is just a number which essentially just says how important they are. So you can make the priority number whatever you want. Usually it makes sense to say the higher priority processes run first, and sometimes that corresponds to a higher or lower number. You just need to be consistent. And then, so we always run higher priority processes first, and then you might round robin processes if they are equal priority. And this can apply to both preemptive and non-preemptive processes. So you can assign processes a priority that's just an integer. You can pick a lower or higher number to mean high priority. Again, that's kind of up to you. Annoyingly, Linux, due to historical reasons, has both. So in Linux, for normal processes, the lower number, the higher the priority. So if it's -20, it's the highest priority, and if it is 19, it's the lowest priority. What also may happen if you have priority and you always prioritize some processes over another is it may lead to another case of starvation when there's a lot of higher priority processes. So that means that you would prioritize the higher priority process, and that means a lower priority process would never be able to run because there's too many high priority processes. So that is another case of starvation, which you have to be like, it's like week 5, like, geez. So you might starve processes if there's a lot of higher priority processes and you always run them instead of lower priority processes. So one solution you can do to combat this starvation problem is to have the operating system dynamically change the priority. So if you're a high priority task and you've run for a long time, well, maybe we bump your priority down to try and be more fair to the lower priority classes or processes. And then whenever they have a chance to run, we can bump up our priority again. So if it's an old process that hasn't been executed in a long time, you could go the other way too and just increase its priority so eventually it gets a chance to run. So with priority is another problem. So we still have that old starvation issue that we discussed before, but now we have priority inversion, which is a new issue. So you can accidentally change the priority of a low priority process essentially to a high one caused by dependencies. So if a high priority process depends on a low priority process, well, it's not going to be able to make process. It would just be scheduled over and over again, and it's essentially blocked on a lower priority process. So if it's dependent on that low priority process to actually make progress on your machine, that low priority process should at least temporarily be treated as a high priority process because a high priority process depends on it. So one solution you could do to this is something called priority inheritance. So if one if one process is doing something dependent on another, you inherit the highest priority of the two processes. And then, of course, you could recursively do this to chain priorities together so that everything that, if you have a dependency chain, they all have the highest dependency. And that way, you can hopefully resolve that dependency. And then whenever that's solved, everything can reset to its original priority. So there's also kind of different tasks are kind of at odds with each other, and they are given names. So there's some people divide processes into what they call foreground processes and then background processes. And foreground processes are generally applications a user's interacting with directly, and background processes you don't really care. They're just doing some computation out in the background. You might not even care about the response time as long as they finish quickly. So in Unix, you can also background processes yourself when the process group ID differs from its terminal group ID, but that's like something you'll never see. If you look in HTOP, you might be able to see those numbers, but that's just like something that's good to know. Essentially just means it's not connected to a terminal. So you do not need to know the specific definition. But the idea again is just to separate processes that users interact with. So foreground processes, you can prioritize having good interactivity and low response time, while background processes, you might just care about, lowering the average waiting time. Yeah.
I have a question regarding the priority inheritance.
Mm-hmm.
So after the inheritance, will the low priority process have the same priority as the highest priority process?
Yeah, so if a high priority process is essentially waiting on a low priority process, that low priority process should be treated as a high priority process just to resolve that. Otherwise, the scheduler would just say, hey, I want to run the high priority process over and over again, and it's not going to make any progress, right?
Are they going to have the same priority?
Yeah, so temporarily, if there's a dependency, the low priority process would inherit the high priority process's priority, and then that way, when it yields, it could actually schedule the one that's dependent on, and then it would do its computation, then resolve that dependency. And then it can go back down to its original priority after it's done whatever the high priority process is waiting for it to do.
Okay, but how does scheduler know who depends on who? They have the same priority.
Yeah, so if they're processes, right, if there's a dependency between them, they have to do some inter-process communication, and that way the kernel knows about it. So the kernel will know that there's communication between those two processes, and then be able to switch the priority temporarily.
Oh,
Yep. Cool. So also, you might be able to use multiple different queues. So if you have foreground processes and background processes, you could treat them differently and use two different scheduling algorithms. So you could just round robin the foreground processes because you care about interactivity and being fair and having a low response time. So you could round robin all of the foreground processes. And then for all the background processes, you could just use first come, first serve if you just want to kind of complete them as fast as possible. And you can't predict whatever the shortest job is running first. But Now, because you have multiple queues, so you have a queue for foreground and a queue for background processes, you also have to schedule between the queues. So when do I queue a foreground, something from the foreground versus when do I queue something from the background? So you could round robin between the queues, or you could treat the foreground queue as having a higher priority than the background queue and kind of trade off between them. And this is where scheduling gets complicated, where there's just no right answers. It's just a continuous series of trade-offs that just kind of feel better. So, like I said, no right answer, only trade-offs. And we haven't even talked about how you schedule for a multiprocessor system. So if you assume symmetric multiprocessing, so remember I showed UNAME before that said SMP, so that's what SMP stands for. It basically assumes that all CPUs are connected to the same physical memory and that they all have their own private cache, at least at like the lowest cache levels of like L1, L2 cache. So that's what symmetric processing means. It assumes all the CPUs are the same, they all use the same memory, and they're connected, or they all have their own private cache. So one approach, if you want to schedule multiple cores on your machine, is just, hey, I'll just use the same scheduling algorithm I've always used. So I just have only one scheduler, but I just keep adding processes while there's available CPUs. So if I have, 9 processes I need to schedule and 10 CPUs, I'll just keep giving those processes while there's still available CPUs. And then as more process comes on, I fill up all the cores. Then I have to worry about switching between them. But while there's still some CPU cores, I can just go ahead and give a process directly to a core. So some advantages of this is it's got good CPU utilization. I'm trying to feed all the cores as fast as possible. It's pretty fair to all the processes, but it's also not super scalable since everything blocks on the global scheduler. Since we know about locking now, this queue would have to be managed by the kernel. And because all CPUs are using it, you can just assume that the queue would have to be protected by a mutex. So it essentially makes it only single-threaded. Yep.
So is it more beneficial on single core systems than multi-core systems, like multi-CPU systems, or is it not necessary?
So this is so for just a single core system, you can just do round robin or something like that, and this isn't a problem. So this is problem specific if you have multiple cores and what you have to do. So if you do have multiple cores, right, you can just can just keep your same queue, your same scheduling algorithm, but just keep on giving processes as you have more cores. So you don't actually have to change that much. But it's not going to be terribly scalable because now you have only a single scheduler and it would have to be protected by a mutex, making it essentially single-threaded. And it's also got fairly poor cache locality because the processes, whenever they context switch in and out, might change between CPUs. So if you context switch a process, in and out on the CPU, it still might have some valid cache entries. So it would actually be faster if it stays on the same CPU. While if you just give it to any old random CPU, you essentially would trash its cache every single time, and it would have to refill its cache. So that's another disadvantage, but this scheduler is actually one of the first ones used. If you go way back and figure out what year Linux 2.4 was out, this is the exact scheduler that's in it. So let's go to the future where we might think of a better idea. So we could create a scheduler for each individual CPU. So now, since each CPU has its own scheduler, there's no global fight over it. They wouldn't have to have a mutex because each CPU essentially has its own queue or its own scheduler. So now when there's a new process comes in, your goal is just, hey, I need to assign you to a CPU, and then you'll stay on that CPU and be bound by its scheduler. So the advantages of this is it's pretty easy to implement. You just take what you implemented before with a single scheduler and just do it as many times as you have CPUs, which isn't too bad. And it's also going to be pretty scalable because there's no fight over any global data structures. You don't have to have a mutex or anything like that. Just one core gets its own scheduler and that's it. And it also has good cache locality because a process is not changing between different CPU cores. So if it gets context switched in and out, it might still have some valid entries in the cache, and that's good because if you don't, you use your cache to speed things up. Disadvantages of this, of course, is that you might have some load imbalance as you use your system. So that may be fairly fair if all processes run for the same amount of time and last for the same amount of time. But you could imagine getting fairly unlucky where you schedule all your short-running processes on a single core and all your long-running processes on all the other cores, and then suddenly that core finishes all the processes and there's no new ones, and then suddenly that core is just sitting there idle and not doing anything. So you can have some load imbalance just from however you happen to assign your processes and however the processes happen to run. Yeah?
Could you explain why this approach has a good cache locality?
So in this approach, at least what we're discussing right now, as soon as you assign a process to a CPU core, it stays on that core.
After the context switch, it won't switch to others.
Yeah, so if it gets context switched out, it would assign, pick another process that got scheduled to that core, but then whenever that process gets scheduled out, it could switch back to the original process. Right, so if you have something like, I don't know, what's some run? Say you have some long-running computation process that's running on that single core. It's running, and then it gets context switched out to run like LS or something. So it would get context switched out, LS would run, do its thing, probably not touch that much of cache because it's not that big of a program, and then it would context switch back in that big computation. And because it context switches back on the same CPU core, it would still have a lot of valid cache entries because it's the same CPU core. So under this scheme, as soon as we assign a process to a CPU, it will always run on that CPU if it gets chosen to. So it'll stay on that CPU and won't move between CPU cores. All right, any other questions? Cool. All right, well, that you can imagine something better that you can compromise between this global data structure and a per CPU scheduler. So you could keep a global scheduler, but just reduce the amount of work it needs to do, so everything's not dependent on it. So you could have a global scheduler that basically just checks if a CPU is idle, and if a CPU is idle, it can do something. It can just steal a process from another CPU core and move it to the idle CPU, just pretty much to put it back to work, right? So if this does happen and you allow the scheduler to essentially steal processes and shift them between cores, well, you might want to control what actually happens. So there might be a process you really, really care about that you don't want to be moved between cores, and they might be really sensitive, so you want some form of control where you can keep it on the CPU core if you absolutely need to. And that is where processor affinity comes in. So every process has an affinity, and basically that just assigns a value to it that says what this process's preference is to be scheduled on the same core. So if it has a high affinity, it would prefer to stay on the same core and not switch between cores. So that's what that means. You might see this too in Windows Task Manager and stuff like that. You can actually set core affinities and when you try and increase your performance, you just, if you have a game or something, you might want your game to only run on a certain core and stay there so it never gets context switched out. And then we can, you can have lower latency and own people. So this is again another scheduler the kernel actually used. So this is like the simplified version of it was called the 01 scheduler that was in Linux 2.6, which is, probably like 30 years old or 20 years old. No, like 30 years old. So we're getting closer to modern times. So another strategy in terms of, bad kind of unfortunate naming conventions is called gang strategy. So this is more for high performance computing. So you might be in the case where you have multiple processes and you might want to schedule them all as a single unit and schedule them all simultaneously. So the scheduler on each CPU can't be completely independent if I want to run all the processes at the exact same time. So you might use something called gang scheduling. It's also might be referred to as co-scheduling. That allows you to run the set of processes simultaneously, and essentially they are all scheduled as one big unit. But of course, this would require a big global context switch across all CPUs because they all need to context switch essentially simultaneously to schedule all the processes. But you will only really find this if you ever go into like high performance computing. So there's also another type of scheduling called real-time scheduling, and it's yet another problem. So real-time means that there are like certain very, very hard time constraints. So either for a deadline or a rate. So for audio is an example of a real-time system. So you have a certain bit rate, you need to keep up with that bit rate, otherwise your audio will sound garbled and it will just be completely trash. So you have to maintain that rate, otherwise you won't hear clear audio and it will essentially be useless. Another thing that might be very important is something like an autopilot. So it needs to react within a certain time period or otherwise your plane crashes and that's no good. So hard real-time systems, there's kind of two types of real-time systems. Hard real-time systems are like, they are absolutely required to guarantee a task completes within a certain amount of time. And that is a very, very difficult thing to do. And typically it's meant for like microcontrollers and things where you can actually count the number of clock cycles that an operation might take to guarantee it happens, within 10 microseconds or something like that. So if you do get into like embedded systems and real-time development, you'll pretty much be using your own little chip, and you will probably not even have a kernel or anything on it. You will program directly on it, and you'll be able to essentially count the clock cycles and figure out that it meets some type of timing constraint. And essentially for any like big kernel like the Linux kernel, you essentially can't do hard real time because it's too complicated and there's too many things going on. So you'd have to argue about the scheduler, when things can be made. You'd have to argue about its runtime in the worst case scenarios where all the caches don't seem to line up, and you'd have to understand everything about a complicated CPU and all that. And it's pretty much impossible. But the alternative to a hard real-time system is you use what's called a soft real-time system, where critical processes just have a higher priority process and your CPU is so fast that in practice the deadline's always met and you just don't really worry about it. So audio might be hard for like a very small embedded microcontroller that runs at like 100 megahertz, but for your big desktop system that runs at like 5 gigahertz, I mean, any audio thing is going to be done so fast that it's going to keep up with the rate, no problem. So Linux is also an example of soft real time, and it's something you can specify when you create processes and when you change their priority. So in terms of these real-time tasks, generally you want the scheduler to be super predictable. So the scheduling algorithms like first come, first serve and round robin that we saw yesterday are actually implemented in the Linux kernel and actually are in use and are perfectly valid scheduling algorithms. So you can actually search, if you're crazy enough, you can go search the Linux kernel source tree and look up them. So anywhere you see Schedule FIFO, that's first come, first serve, and Schedule round robin is round robin. And you can see exactly how they implement it and see exactly what's going on. So it's as you would expect. And what they do is use kind of a multi-level queue scheduler for processes with the same priority if they're soft real-time tasks. So it will always do tasks of a higher priority before doing a lower priority task. And it would use, first come, first serve or round robin as you see fit. And then that would also do what we said before where, to avoid starving processes, the operating system can kind of dynamically adjust the priority if it's taking way too much time. So on Linux, there's going to be two types of processes. There is soft real-time processes where it always schedules the highest priority process first. And then there's normal processes that adjust priority based off aging and do some other things. We'll see the actual scheduling algorithm. But this is enough to see, to kind of understand what the priorities are and understand what top is telling us. So on Linux, the soft real-time processes are always prioritized, and they'll either be scheduled with first come, first serve, or FIFO, or round robin. And there's 100 priority levels, and due to historical reasons, they're given the priority 0 to 99, and this is where things get weird due to historical reasons. So with these 100 static priority levels, 0 is lowest priority and 99 is the highest priority. And then, so those are soft real-time processes, and then the Linux kernel also separates that from normal processes where the normal scheduler runs, which if it's an older version of Linux, it runs that 01 scheduler. So other processes would just be under the schedule normal flag, and by default, their priority is a 0. And the priority ranges from -20 to 19, where unfortunately, -20 is the highest priority and 19 is the lowest priority. So processes can also change their own priorities with system calls, nice and set scheduler. And let's go ahead and see some processes in our VM. So now we can actually read this, kind of. So in here, can everyone read that, kind of? Yeah. All of it. Can you, all right. So let's follow my cursor. So here these are all the processes and threads running on my machine or on my VM. And we see the first process here is PID 1. So that is a init. And we can see it's systemd. And then, so that's at the first column, what the process ID is. And then there's some others. There's user. So the user of the first priority, or the user of the first PID 1 is root. And then PRI is its priority, which is on kind of a big global scale. And this is where things get kind of weird. So its priority is a 20 on the global scale. And then there's this NI, which is its niceness. And they're separate. So the niceness falls under that normal scheduling. So a niceness number will be between -20 and 19. And yeah, so a niceness will be between -20 and 19, and by default it will be 0. So its niceness of all the processes I see here are all 0, so they're all the default priority and they're all normal processes. So if I look through them, so I'll just look at this PRI column and this nice column, or the NI column. If I look through all my processes, and here, if you look at the command on the right, all of the text in white means it's a process, and if it's in green, it means it's a kernel thread. So for example, this process GDM here, this process has 2 extra kernel threads in it. So let's go through and see if there's anything with interesting priorities. So here's this process. So this process, its niceness is a 1, so it's a slightly lower priority so it's a slightly lower priority, but then if we look down 2 more, we see that this RT-kit daemon, its priority is RT, which is real time, which is the absolute highest priority. So the kernel would schedule that before anything else if it wants to run. But for the most part, it's just sitting there sleeping and it's blocked. So annoyingly, I'll just illustrate this. So the priority column, that PRI column, is essentially this line on the bottom here. So the priority line on the bottom is essentially a way that for the kernel to unify normal processes and soft real-time processes. So it essentially takes all the priorities from normal processes and soft real-time processes and places them on the same number line, where the lower number, the higher the priority. So everything falls on the same number line, and then all the normal processes, which are over here, on the right, essentially map to positive values on this global priority line. So if you're a normal process that is between -20 and 19, it essentially just shifts it up so that on the global priority line, if it's 0 or above, it's a normal process, and if it's negative, it's a lower priority. Don't ask me why, it's kind of weird. And then for the soft real-time tasks, that should have a priority of 0 to 99, where 0 is lowest and 99 is highest. To map it back onto this to make it make sense, it essentially makes it negative and then subtracts 1 from it. So if it's a 99 in like the soft real-time process on the kind of unified line, it would correspond to a -100. And if it is 0 soft real-time, so lowest priority, it would correspond to a -1. So if we go back here, if we see any negative numbers in the PRI column, that means it's a soft real-time one. And unfortunately, if it just says RT there, it means it's a -100. And in that case, the niceness doesn't really matter. All right, any questions about that to read this? Because it's kind of weird that they do that. So for the most part, the lower number, the higher the priority, except if it's, the historic soft real-time things where the higher number is higher priority, and then they just make it negative. Why? I don't know. All right, any questions on that? We can explore. Okay, so cool. There's a real-time task here. Let's go through and see if there's anything else interesting. So here we can pick off, this is a normal process because its global priority is 39 and its niceness is 19. So it's the highest number, so it's the lowest priority. So essentially, GNOME shell has a thread that it doesn't really care about. Yeah, so also going back to this, so essentially the niceness number only applies if it's a normal process. So if the priority is 0 or above, niceness applies. Otherwise, the niceness number, if it's a soft real-time, doesn't really apply and you can kind of ignore it. So for this real-time one, its priority is -100, so it's soft real-time, and we can kind of ignore the niceness. So hopefully that answers the chat question. So let's go explore. So there's one thread in GNOME shell that apparently it shouldn't care about because it has a niceness of 19. So we go through here. There's another thread here in my shell that doesn't seem to matter. And let's see if we can find anything else. Yeah, so when it's a soft real time, so the priority column is negative, the niceness essentially doesn't mean anything. So here we go, we have some more things. VS Code wants apparently 44 gigs of memory. That's cool. Holy crap, there's a lot of processes running. So here we can see, so here, process ID 2, and it doesn't have a parent, so this is an internal kernel thread. So we can actually look at some kernel threads. So there's an internal kernel thread here that has a normal priority, and it has some higher priority things that are just kind of scheduled as a process. So, which you can read what they do. It's not super entertaining. And then there are some high real-time kernel threads here. So there's this migration, which essentially is doing the context switches. So its priority is real-time. So if it needs to context switch, it's a very high priority. So there's going to be one of these per CPU. So this is, the migration for core 0. Then there's one for core 1, core 2, and core 3. So they're all scheduled as real-time because they're very, very important. And I think that's pretty much it. Oh, finally here, this watchdog one. So its priority is -51. So it's like we half care about it. It's a soft real-time, but it's not like the most important real-time, but we kind of care about it. So you can just kind of go through and see, we can actually read these numbers now and understand kind of what the kernel's doing. All right, any questions about this fun adventure through HTOP? Cool. Yeah.
Could you scroll up a little bit when there is a priority is about 30 something?
Priority above 30?
Yeah.
Here?
Scroll up a little bit. The example we just talked is 34 or 30.
39?
39, yeah, 39. So why you said this has a low priority?
So it's just, so the higher the number, the lower the priority in this. So
For priority column, if the number is larger, it means the priority is lower.
yeah. Yeah, so the priority number in the third column there corresponds to this big global priority number. So this is like the global priority for the Linux kernel, where if it's negative, it's soft real-time, and if it's 0 or above, it's a normal process. And then this annoyingly is the soft real-time priority, which was between 0 and 99, where higher meant a higher number. But for all the Linux to kind of unify everything, they just use a big global priority number, where lower is higher priority.
And we don't have any approach to see the soft real-time priority in that table.
In what? Yeah, we saw it. So when we saw a -51, and when it says RT, that means -100. Yeah.
And the niceness is the same as the one shown in the table.
Yeah, so niceness corresponds to this -20 to 19, and then it would just be shifted on the global priority scale. So they'll always be off by the same amount. So if the priority is, 0 or above, you just subtract 20 from it, and that's its niceness. Well, yeah, so for historical reasons, they just did it like that. Yeah, so you just ignore nice priority when it's negative and it's a real time. Niceness doesn't mean anything then. Okay, so this is going to be the Linux scheduler evolution. So we saw that ON, that global queue, it was simple but had poor performance on multiprocessors and with many processes. Then in 2.6, there's that per CPU scheduler that was called O1 that was fairly complex to get right and had interactivity, also had issues, and it had no guarantee of fairness. So that was that one that could steal processes between cores and move them around. Then since 2.6.23, which is the current scheduler, they opted to create something called the completely fair scheduler, or CFS, and it is fair, allows for good interactivity, and it's been used for like the last long time. So the O1 scheduler has issues with modern processes. So it would have been nice if you could actually separate out foreground and background processes, which was easy with a terminal, so you could tell what processes are connected with a terminal. But nowadays we have GUI applications and you can't always tell if they're connected. You don't know if the user has them focused. so on and so forth. There's a lot you don't know that the kernel just can't know about the processes, so it can't help with scheduling them. So if you're the kernel, you could try and detect them. So you could try and make some heuristics that try and determine whether or not a user is interacting with a process or not. For example, you might assume that processes that sleep a lot might be more interactive. So they like interact with some keyboard input, do something really quick, and then go back to sleep. So if you detect a process behaves like that, you might be like, I guess it's an interactive process. Maybe I'll prioritize this in my scheduling a bit more. But it's kind of ad hoc and could be fairly unfair, and you could also guess wrong. So if you want to introduce fairness for different priority processes, what you could do while still being slightly fair is to use different size time slices. So we essentially will give higher priority processes a proportional more CPU time, but still have low priority processes get at least some CPU time to be fair. So this is better, but is also kind of ad hoc and hand wavy. You're just kind of guessing. Ad hoc? So ad hoc just means I'm just guessing. Like it's just a complete shot in the dark. I'm just making something up. It's just a fancy way of saying I'm making something up. So when you make something up, you might want to consider the ideal situation. So with like ideal fair scheduling, you could assume that you have an infinitely small time slice, and then if you have n processes, you would just give them each 1 divided by n of the total CPU. So if you have one process, you would just give it the entire CPU time. And then if you have 3 processes, you just divide it up equally between them, give them all a third of the CPU time, and then everything's completely fair. So it would be evenly divided along every processes. You can't get any more fair than that. So here is some scheduling. So if you have 4 processes come in at the same time, t equals 0, and they all have different burst times, thankfully a multiple of 4. So process 1 takes 8 time units, process 2 and 4 take 4 time units, and then process 3 takes 16 time units. So just to make this easier, each vertical slice here is going to be 4 time units, and each box represents, one of those time units. So at time 0, if I want to be completely fair and divide up my 4 units of CPU time, I would give each process a single unit of CPU time. So each of my processes would execute for 1 time unit. So process 1, 2, 3, and 4 each execute for 1 time unit. Then for the next 4 time units, I let them all execute 1 more because they're not done yet. So they all have executed for 2 time units now. Then I do this again for 3 and do it again for 4. Then after 4, there's only going to be 2 processes left. So I can give them each, divide up that 4 and give them each 2 time units of CPU time. So if I do that after t equals 16, why can't I highlight it? After t equals 16, process 1 and 3 both get 2 time units, so they have executed for a total of 6 time units now. And then if I'm being completely fair, there's still 2 processes, so I give them each 2 units of CPU time. So now P1 is done after its time units, and now since I only have 1 process left, it can get all 4 time units. So it would go from 8 to 12 because it's using all the CPU cores at this time, or all the resources at this time. And then it would do 16 and it's done. All right, does that make sense to everyone? I'm being completely fair here. So it's fair, but it's also insanely impractical that each process gets the same amount of CPU time. It would boost interactivity because it has the ideal response time. It just assumes infinitely small time slices and goes immediately. But in practice, you can't do things instantly, and context switches take time. So this just wouldn't happen because there'd be way too many context switches. And you also have to constantly scan all the processes, which is O(n). So every single time I have to scan all the processes, give them all an equal share of the CPU time, and then switch between them, and it's just not feasible at all. So this is where the completely fair scheduler comes in. So for each runnable process, you assign it a virtual runtime. And then at each scheduling point where a process runs for some time slice, you increase the virtual time by however long it actually ran for, then times a weight based off its priority. So if it's lower, if it's a higher priority task, which corresponds to a lower number, it would increase that virtual runtime by a smaller amount than a low priority task. And then because of this, the virtual runtime monotonically increases, which is just a fancy math word. Monotonic functions, it just means they never decrease. So it will only ever increase or stay the same. So the virtual runtime never goes down, it only increases. So then what the scheduler does is, all it does is select the process with the lowest virtual runtime. So, and then it computes how long it needs to run for, how long its time slice is, kind of based on what would be ideal based off the number of processes currently running on the machine. So then it allows the process to run for whatever time slice it determines, and then when the time slice ends, it just repeats the process. So after its time slice, it would have increased its virtual runtime, and then the scheduler would run again and just pick whatever process has the lowest virtual runtime. So your completely fair scheduler would be implemented with a fun red-black tree, so those are actually used. So you probably learned that did we learn that before? All right, we learned that yesterday, so now we see where it's actually used. So they use a red-black tree for the completely fair schedule. We all know it's a self-balancing binary search tree. So it's keyed by virtual runtime, which only ever increases. So if you insert a process when it's done its time, or need to delete it when it's dead or update it, that's logarithmic time. And if you need to find the minimum, which is what the scheduler does, right? Whenever it needs to make a scheduling decision, it just picks the lowest virtual runtime. So that's just 0.1, that's super, super fast. So that's why the scheduler would use it. So the virtual runtime, it keeps track of everything on like nanosecond level granularity. And that way it doesn't need to guess the interactivity of the process. It just kind of nicely fits in this. So it will tend to favor IO-bound processes by default because they just essentially have little short bursts of CPU time, which would translate to like a low virtual runtime. So they only run for like, maybe a few microseconds and then give up their time slice voluntarily. So they wouldn't have increased their virtual runtime that much. So whenever they get new input again and are ready to run, they would have a very low virtual runtime and would probably be at the top of the tree and then would be scheduled to run immediately. So it gives you it essentially prioritizes those tasks to let you have really good interactivity with them. And it just kind of falls out of how the scheduler is implemented. All right, so does that make sense? Cool, so good timing with red-black trees. So now scheduling gets even more complex. We got more solutions and more issues. So we introduced priority, and that was good and bad because it also introduced priority inversion, which is not a good thing, and it's just a more complicated thing to deal with. Then we saw that some processes might need good interactivity, others you might only care about whenever they finish, and you might want to distinguish between them. Then we saw what happens if you need to scheduler across multiple CPU cores, and one solution is just to make a scheduler require per CPU queues or schedulers for it. Then we saw real-time briefly, and it requires being predictable. And then finally, we saw the completely fair scheduler, which is actually used by the Linux kernel and essentially everything else, and that tries to model the ideal fairness. And that's it. So just remember, I'm pulling for you. We're all in this